Greetings. This is the second week of lectures that I'm going to record today. Uh, and I'll try to do this in two installments just to make sure that I don't run over my time on YouTube. Uh, so the first week we talked about the fetch, decode, execute process. And then we used VESP 1.0 to illustrate what these steps actually mean. And so what I'm going to do, I'm going to start out directly with the fetch steps that we covered last week so we can transition to decode and execute steps of the fetch, decode, execute cycle. So here you see what we already have covered in the first week that we did our classes. And the fetch process takes basically 3 clock cycles, as you will see by these pulses that are put together here. And what really happens is very quickly that we transition from what we call the rest state, the initial state, to a state where we do load a program counter into MAR and then increment program counter for the next instruction to be fetched, and that takes 1 clock cycle basically. And so that 1 clock cycle is consumed effectively by this flip-flop. And then by the time that ends, that time period, that clock cycle is consumed, then we go to the next step where we now use the address which we have loaded from, copied from PC to MAR to actually go and grab the instruction from the memory. That's what this second process here, the second clock tick will help us accomplish. So when we get this done, we will then have, by the time we're actually here at the end of this clock cycle, we would have reached this place. And with the ticking of this clock cycle here, we would actually have the MDR, which now holds the instruction, copied into IR. And that's where we're supposed to have the instruction in order to decode and execute it. So as you will see on the next slide, what we do, we take that instruction and at the same time I make this incrementation of the MAR. You will see that this will be useful to expedite, actually shorten the process of execution for the load and the move instructions as they come down, not on this slide but the slides that will follow. What is happening here is that now that we have gone to the point where we want to copy MDR into IR, and for that we need a clock cycle to elapse. That happens, and by the time we get here, we do have our IR, hold the instruction. So this is really where we have the instruction in the IR right here. This is where the initiation of that process takes place. This is where the actual copying is completed. That's how these clock ticks work. We kind of look at the output end of the flip-flop to materialize what we really want to accomplish. That's how I at least write these expressions in here. So given that convention, now we are at a place where we could actually, that is to say, we have the instruction in IR. We can now proceed with the execution. And to be able to do the execution, we have to look at, now interrogate the opcode of our instruction, which of course are available to us within the 3 bits on the leftmost side of the instruction register. We have these bits 0, 1, 2, and by subjecting them to a 3 by 8 decoder, we get to sort of like decode what instruction it is that we want to execute on VESP. So in this situation, the decoder, of course, will only fire one of these 8 outputs, depending upon what comes in. And I've just used these 3 tuples to indicate, what these outputs signify. So the first possibility that all 3 things are 0 here, bits, and that is what we define as an add instruction, which is the topmost wire here. So with that wired in here, and the fact that we happen to be here in Q4 state, we are ready to go out and do the add, which is basically what this arrow indicates. And instead of having 0, 0, 0 here at the output of the decoders here, that the second output is fired, if that is the case, that means we have a pattern which is like 0, 0, 1. That would then mean that we're going to complement instead of add. And that is what this AND gate together with this output accomplishes. And so that's the complementation. And the other remaining 6 instructions will be taken care of by these choices here that we may encounter depending upon what the instruction that we want to execute. And incidentally, once we complete these steps, our execution is over for these 2 instructions. Of course, we only do one or the other. We never do both of them at once. And so all that means that we have to go back, and this wire here is actually so like heading back to the very beginning, which will be, I guess, right here. So that will be like 1, 2, 3, 4, 5 clock cycles, at the end of which we go back to the beginning. And so then the rest state kind of separates this process from the next instruction fetch, which is going to take place here. So this is connected exactly to this place, meaning that we just completed our execution, either this operation or this operation. Now we go back to fetch the next instruction, because we had incremented the program counter here, so when we get back here, it will be the next instruction. In this case, of course, we don't have to worry about changing the program counter again. That's just this step, these 2 instructions. Now for the next 2 instructions, we're going to have to do something slightly different. The thing that we actually get to do is, this being a load instruction, we just have to remember that the load instruction has some address which is sitting within the instruction word itself, and also some data. And the data actually is the operand that is held in the next 16-bit locations. So the first thing that we do when we get to this point where we're now executing a load instruction, and then the LDA is 1, meaning that this wire is actually 1 right there. That is the combination of the 2 ended together that gives us a 1 over here. And this is what we then do. What we do is we take what we already have incremented, which is what our MIR here is. As you know, that I just told you that we actually did this incrementation in this step, So we moved the pointer to the next location that follows the instruction word. And now we're going to copy that operand into MDR. And then while we do this, we also condition MAR with the address which is held in the IR register, and then of course we pad it with 0 so that it becomes 16-bit address. And then we go in and write. Now one thing that I seem to have forgotten here is, in fact, we have to increment the program counter by 1 here, only because we would have to go and fetch the instruction from the next location down, not just this operand which we actually fetched and placed in the address, the location that was pointed by the address in the instruction. So this incrementation of PC has to take place here, because we incremented the program counter at the very beginning, right there, as you see. But that's just like going to move it down to the next location, in this particular case, the instructional LDA. And we really cannot do that, because in that next location we do have the operand, and that's what we just fetched by way of this first incrementation of MAR. So what we're doing here is just incrementing the program counter a second time, because we want to go down 2 locations from the instructions location just to get at the next instruction. There's that other word in between. So this completes the execution of the LDA instruction, and then we go back to the same step D1. That's always going back to the same place. Alright, so the move instruction is a little more involved. It's just this reading will be repeated 1 more time. We'll have 2 reads as opposed to 1. But we condition the MAR initially by incrementing it by 1, so we still are going to go out and get that second operand by way of this read with the move command. And now that we got that, what we do, of course, we move it into MAR. That's the next step. and then we do a second read. And then while we do this, we also condition the MAR to the address, which is still held in IR because we haven't changed it. And now that we've done that, we can actually go out and do another read. But the same way that we missed the program counter incrementation, I need to increment the program counter here one more time. Let's see if it's going to fit in there. If not, I'm going to have to stretch it a little bit, but then it will probably destroy this. And I have to bring this a little bit this way. Maybe some room there. And this moves up a little bit closer this way. And I think I'm kind of almost done there. Almost. Just another tidbit there, but let's see how this actually works. And maybe just push it up a little bit so we don't get those mixed up. All right, so that is your move instructions execution. You know, 2 reads and a write, but then the program counter has to be incremented. Sorry about this. And that incrementation, of course, is just to prepare for the instruction that follows. Okay, so that just takes care of this. Now, what else is left? The jump instructions, and we can actually bundle them together because they're kind of the same thing. So again, we are in Q4, state Q4, it's the same place. But now we have conditions with which we could jump, or we have a force jump on us. That's the first case, that's the jump case. The second case is jump with a 0, so the 0 flag has to be 1. Not just we want to jump with a 0, but we want that flag to be 1. And the third case is we want to jump if what AC is, the accumulator is, if the accumulator is positive, or we want not 0 and not negative condition simultaneously satisfied, so we know that whatever we have in the accumulator is positive. Any one of these conditions will actually trigger a change in the program counter. That's what a jump means. And so we load the program counter with the instruction, the address that is held in the instruction, of course with padded zeros on the left. So that completes the execution of those 3 instructions. And then we have the halt instruction. That's the last one. So all we do with the halt instruction is to reset the machine. That's all we do. And what this reset does, it brings the machine to basically the rest state. And that's what we want to do. And when that happens, when we're in that rest state, then we're going to continue with the execution of instructions as they come down the pike. That is to say, as we actually have programs get loaded onto VESP and then executed instruction by instruction. Let's see if I can actually continue a little bit further here, and that by talking about data path design, we briefly covered what we would really have to do in order to get the A register design. So I'm going to go over that fairly quickly. But what I show here, what I actually indicate here, is this table where the check marks indicate the source-destination relationship between these registers that I've marked down here. For example, A feeds itself but doesn't feed anything else. It doesn't feed anything else. IR, this is what I recollect. Just imagine, what the transitions are. Those steps that we covered in the fetch, decode, execute process. IR actually feeds PC. We might be going from the IR to PC as well as to MAR. It looks that we might be taking things out of IR and put them into MAR. I'm just thinking that, let's see where that would happen. There is an address in there, which may actually go directly to MAR, just to be able to fetch something or store something. And then the PC feeds PC itself because we increment PC, and also goes to MAR as we saw at the very beginning of our fetch process. MDR goes into IR that we saw during the fetch process. It also goes to MAR during the move instruction. MAR doesn't go anywhere. It actually takes things from other places, as we saw lots of places. And then the B can be combined with A for an add operation. So this table kind of like succinctly summarizes how interactions, what interactions are there between these various registers of VESP. So this could be a different computer, this could be a different data path, but the idea is the same. You want to know exactly how these transitions take place. Now this approach that I'm actually outlining here is called a register-based design, data path design. Everything kind of like hovers around registers. There is also what's called a bus structure-based data path design, and we'll cover that when we talk about microprogramming. That will happen later on. So this particular sort of method that I'm using here is the data path method, is actually what's called a register-based design. So what we're going to do, we're going to basically take each and every one of those registers. So in this situation, I'm just looking at the A register itself, and it's 16 bits as you remember. And then I'm going to take a typical flip-flop and just basically design that flip-flop. And once that flip-flop is designed, then the rest of the flip-flops will be identical. Now, in some cases, the flip-flops on the edges, like on the leftmost or rightmost positions, might actually be designed differently, like in the case of shift instructions, for example, which we don't have in this case. But here, this is just not going to happen with A in this situation. We have basically two different things that we do with this A register. Either we complement it or we add. Now it seems like I've got some extra characters here. It's just one that should not have been there. And this also should not be it's just like comp is what I need. So I make mistakes like this, as I told you. Sometimes it helps you to actually understand things a little better, because you see the kind of mistakes that I made in typing things here, and then you know that by going over this, you understand how things are supposed to be. The I is like the index for the flip-flop. This is the ith, if you like, flip-flop. So, if you think of these flip-flops running from left to right, register is going to be something that's going to have lots of these. I can draw something here. Let's see if I can actually take this one, for example. Just one of these things. Let's see. If I just go ahead and do this, it'll take some time. I'll just delete this. I'll just delete this whole thing. So what I'm saying is that if you stretch this and then put all these, make it basically like so. This becomes our registry here, and this register has, you've got. I gotta go here and then make some changes. If I can pick a line here. So you got a bunch of these here. Let me see if I can draw one there. So we're talking about a register space here, okay? And this ith one is there somewhere in there in between. Okay. I could just align these. Align their bottoms. Let's see if it actually exceeds somehow. Maybe group them. And make them a little smaller. Okay. Maybe so. So this is like the ith one, maybe, right somewhere in there. One of these registers is the ith one. Like this is one, the second, and then the last one. That's how it goes. All right, so this is just a simple design. I'm going to get you a homework problem where you will work on not the A register, which we just have done here, but on the other ones. So that is AI. This is AI, BI, and CI. So what is CI? It's the carry. Again, write this down so that you don't really question this later on. Okay, so CI is basically the carry bit for this particular level. Now, those of you, and I know that you all did take ENEE350-Week, so you know what this is anyway. So that's the carry bit, and then of course AI and BI are the bits that are the bits for the A and the B streams that are the two operands. So I think it may be a good timing here to pause and then maybe do the second part in just a little bit. So this way we secure this now. And when I finish the second installment, I will then assign you a new homework set. All right, until then, take care.